In this lesson, we're going to talk about the Bernoulli, the binomial, and the geometric distributions. They're all related, so I've lumped them together in one lesson. A Bernoulli random variable is a random variable x with the following distribution. The probability that x equals 1 is p, and the probability that x equals 0 is 1 minus p for some p between 0 and 1. And for such an x, we say that x is Bernoulli p. So a Bernoulli random variable can be thought of as the outcome of an experiment. Whenever the experiment is successful, we say x equals 1, and the probability that it is successful is p. If the experiment fails, we say x equals 0, and the probability that the experiment is going to fail is 1 minus p. We're going to find the expected values and variances of these random variables. So first up, I guess, is the Bernoulli random variable. The expected value of x is, well, it's 1 times p plus 0 times 1 minus p. So it's 1 times the probability it's 1 plus 0 times the probability it's 0, which is just p. So p is the expected value of x. And the variance is the expected value of x squared minus the quantity of e of x squared. So we get 1 squared times p plus 0 squared times 1 minus p minus the expected value squared, which is minus p squared. So these first two terms are related to this e of x squared. And this last minus p squared is the minus e of x squared because e of x is p, as we saw above. And this gives us p minus p squared, or p times 1 minus p. This is the probability of a success times the probability of a failure. Now on to the binomial distribution. So a random variable x has the binomial distribution if the probability x equals k is n choose k times p to the k times 1 minus p to the n minus k. Here n is a fixed number, it's a positive integer, and p is some number between 0 and 1 again. So we would write this as binomial np. And n is So this is like running more than one experiment. For the Bernoulli, we have one experiment, and either it succeeds or it fails. For the binomial, we now have n experiments. And the probability that x equals k is the probability that exactly k of the experiments succeed when the outcomes of all the experiments are independent of one another. So this p, the success probability, is to the k because we have k successful experiments. And then the other n minus k of the experiments fail. So there's 1 minus p to the n minus k. And any k of those experiments could have succeeded. So we have n choose k experiments that we choose to succeed. So it turns out that if x is binomial np and y1 through yn are independent random variables with Bernoulli p distribution, so the same p here is x. And notice that there are n of them, so we have y1 through yn. Then the probability x equals k is the probability that y1 plus y2 up to yn equals k. In other words, the sum y1 plus y2 up to yn is binomial np. So each one of these is the outcome of one experiment, and they could be zeros or ones. And if we add them up, that's like running n experiments, each with probability of success p. So this is what I had just explained a minute ago. So for example, let's say we fix a particular k between 0 and n, and we want to find the probability that k of the experiments succeed, exactly k. Well, one way that k of the experiments could succeed is that the first k experiments all succeed. So y1, y2 up to yk succeed, and the rest of them fail. So yk plus 1, yk plus 2, and so on, down to yn, all fail, so they're all 0. Then the sum y1, y2 up to yn does equal k, and the probability that this happens, the probability that y1 is 1, y2 is 1, up to yk is 1, and the rest are all 0, so here's our 1s and here's our 0s, is the product of the probabilities from I equals 1 to k, the probability that yi is 1, times the probabilities of the yi being 0 from k plus 1 to n because of independence. So it is important that these are independent. Don't ever forget that condition. And so this is p to the k and 1 minus p to the n minus k. So as I talked through just a second ago, it doesn't have to be the first k that succeed, it could be any k, and there are n choose k ways to have k1s and n minus k zeros. So now let's compute the expected value and variance. It's a lot easier to compute the expected value and variance by writing a binomial NP as a sum of Bernoullis. So we're not going to use the formula for expected value to find the expected value. For a random variable with binomial NP distribution, we can write it as the sum from 1 to n of yi, where each yi is Bernoulli p. And by definition of the sum, or well, actually a result of the sum that we had, you can see in the lesson on expected values, you can bring the expected value inside the sum. So the expected value of the sum from 1 to n of the yi's is the sum from 1 to n of the expected value of the yi's. Now we just saw 1 second ago that for a Bernoulli p, the expected value is p. So we get the sum from 1 to n of just p, which is n times p. So the number of experiments we expect to succeed is the number of experiments we run times the probability that each one succeeds. For a simple example, let's say we run 20 experiments and we expect each experiment to succeed with probability 1/2 and independent of one another. Then of course we would expect to have 10 successful experiments. So we take the number 20 multiplied times a half, the chance that they succeed, and we get 10 as our expected value. We'll also do the same for the variance. So the variance is the variance of the sum from I equals 1 to n of the yi's, and it can come inside because the yi's are independent. So this is the sum from I equals 1 to n of the variance of the yi's, and the variance of a Bernoulli is p times 1 minus p. So we get the sum from 1 to n of p times 1 minus p, which is n p 1 minus p. So it's n times the probability of a success times the probability of a failure. The last distribution we're going to talk about is the geometric distribution. And a random variable x has the geometric distribution if the probability x equals k is 1 minus p to the k minus 1 times p for k bigger than or equal to 1. So how is this related to the Bernoulli random variable? Well, if we run a sequence of experiments and look for the first successful experiment, then we're looking for the minimum number n such that yn equals 1 in a sequence y1, y2, y3 of independent random variables. And that's equal to the geometric distribution. So the way you think about a geometric distribution and the time you'd want to apply a geometric distribution is when you're looking for the first successful event out of a sequence of events, or a sequence of independent experiments that all have probability p of succeeding. So this 1 minus p to the k minus 1 represents k minus 1 fails, and then there's a p, which is the pth success. One simple example would be free throws, maybe. So if you're familiar with basketball and you're shooting free throws, if there's a 70% chance that you can make a free throw, the probability it takes you 3 shots to make your first one would be, well, you miss twice, so you'd have 0.3 squared, and then your probability of success is 0.7, because you're a 70% free throw shooter. So it'd be 0.3 squared times 0.7 is the probability that it takes 3 shots before you hit your first free throw. So now we're going to compute the expected value and the variance, and unfortunately the minimum doesn't behave so nicely with the expected value, so we're just going to use the definition of expected value. And the expected value of x is the sum from k equals 1 to infinity of k times the probability x equals k. So we're summing over all non-zero, we're summing over all values where x has non-zero probability. And this is a sum over from 1 to infinity of k times 1 minus p to the k minus 1 times p. And that p can be pulled out because it isn't being summed. It's just a term that's in every summoned. And this one, if you haven't seen this before, might be a little bit of a trick to evaluate, but what we're going to do is take this and write it as a derivative. So k, p, 1 minus p to the k minus 1 is the derivative of negative 1 minus p to the k. So these two things here are equal. Okay, so we've written this as a derivative. Now a derivative can be pulled out of a sum. So we're going to take this derivative and pull it outside of the sum. And now we can sum 1 minus p to the k. So this is a geometric series, and it's like doing the sum from I equals 1 to infinity of r to the I, where here r is less than 1, the absolute value of r. And so we're going to have r over 1 minus r. And in this case, r is 1 minus p, so we have 1 minus p over 1 minus 1 minus p, which is just p. So this sum is evaluated to this by using this geometric formula. Then we have to take the derivative. So that's negative 1 over p squared, and the negatives cancel and the p cancels, and you're just left with 1 over p. So the expected value of x for geometric is 1 over p. So if the probability of a success is a half, then you expect about 2 tries before you succeed. If the probability of success is a third, you expect to take about 3 tries before you succeed. So the expected value is a little bit intuitive that way. To find the variance, we need to find the expected value of x squared, and it's done in a similar way to the expected value of x. So we're looking at the sum from 1 to infinity of k squared times the probability x equals k. And again, the probability x equals k is 1 minus p to the k minus 1 times p. And here we're going to write k squared. So k squared is k times k, which is also 1 plus k minus 1 times k. So it's kind of a funny rewrite because the negative 1 and the 1 cancel, but we're going to write it that way. So it's 1 plus k minus 1, and then times k is the same thing as k squared. So that takes care of that one. Let's see, so now what we're going to do is distribute k times 1 minus p to the k minus 1 times p to each term. So we're going to take this and distribute one of them to this 1, and one of them to the k minus 1. So we have k times 1 minus p to the k minus 1 times p plus k minus 1 times k times 1 minus p to the k minus 1 times p. And this part here was just the expected value of x that we solved above. So this is just e of x. And so we need to find the sum of the other part, k minus 1 times k times 1 minus p to the k minus 1 times p. Well, we're going to factor out a p and a 1 minus p. So we get k minus 1 times k times 1 minus p to the k minus 2. And it's a k minus 2 now because I pulled out a 1 minus p here. And this, you can check for yourself, it's the second derivative of 1 minus p to the k. So if you take the second derivative of 1 minus p to the k, you'll get a k minus 1, and you'll have a 1 minus p to the k minus 2. The chain rule will bring out 2 negative signs, but those will cancel. And once again, we pull the second derivative out of the sum. And now we're summing 1 minus p to the k from 2 to infinity. So we get, where did I get that 2 from? Oh, right, because if we plug in 1 into this, we just get 0. So we're going to go from 2 to infinity and drop the term that's a 0. So whenever we sum from 2 to infinity, we get r squared over 1 minus r, right? So the sum from I equals 2 to infinity of r to the I is equal to r squared over 1 minus r. So we get 1 minus p squared over p. Then we have to take two derivatives of that, which gives us 2 over p cubed. And after doing a little bit of cancellation, you get 2 times 1 minus p over p squared. Looks like the only thing that cancels is p. Then we get a common denominator, so multiply by p over p, and you're going to get 2 minus p over p squared. Now for the variance, we need the expected value of x squared minus the expected value of x quantity squared. So this is the expected value of x squared, and then the expected value of x was 1 over p, so we're subtracting 1 over p squared. They already have a common denominator, so we just need to subtract 1, and it's 1 minus p over p squared. In other words, the probability of a failure divided by the probability of a success squared.